Picture a vast digital universe. We're talking glowing cities of computation stretching all the way across the horizon. Millions of global transactions are flowing, validators are coordinating seamlessly, and blocks are extending endlessly into the digital distance. But then, the entire system just suddenly freezes. The blocks stop. The network chokes.
Why did it freeze? Well, every blockchain you've ever used, from Bitcoin to Ethereum, was built on a simple assumption. One blockchain should do everything: execute transactions, reach consensus, store data, secure the network. For years, that idea defined the entire industry. But what if that assumption was actually wrong? What if the biggest obstacle to blockchain scalability isn't speed, fees, or even consensus, but the architecture itself? Right now, a completely new design philosophy is quietly reshaping crypto from the ground up. Instead of forcing a single chain to handle every task, it breaks blockchains into specialized layers, each responsible for a different function. Supporters believe this could unlock massive scalability without sacrificing security. Critics argue it introduces new risks and complexities. Yet some of the most important projects in crypto are already moving in this direction. So why are blockchain architects suddenly abandoning the model that built the industry? Let's find out.
Before we dive into the details, please note, this video on the channel Block Spawns Funds is created for educational and informational purposes only, and does not constitute financial or investment advice.
Okay, let's get into Section 1, the Monolithic Illusion, Deconstructing the Machine. To really understand how we fix this machine, we have to descend right beneath that frozen block to look at the systems running underneath. You see, for a decade, foundational networks were built on this all-in-one assumption called a monolithic blockchain. It basically means every single node in the network has to do every single job. And sure, it's highly secure, but it creates a heavily constrained environment. It's kind of like forcing a single-lane dirt road to somehow handle the traffic of a 10-lane superhighway. So what exactly are those jobs? Well, there are 4 core functions of any blockchain. First up, execution. This is where smart contracts run like little engines, actually modifying the state of the network. Second is settlement. This is where validators converge on a single version of reality and resolve any disputes. Third, consensus, simply agreeing on the order of those transactions. And fourth, data availability. This is the guarantee that all the transaction data is accessible to everyone. In a monolithic chain, all 4 of these are vertically stacked and handled by the exact same computers. Which brings us to Section 2, the system break, straining under pressure. So, what happens when global demand suddenly spikes? The system strains and costs just absolutely skyrocket. You've probably heard of the blockchain trilemma, right? It was popularized by Ethereum co-founder Vitalik Buterin, and it highlights the inherent trade-offs in blockchain design. The rule of thumb is, if you want to maximize speed and scalability, you almost always have to sacrifice either the security of the network or its decentralization. A single network simply cannot optimize for all 3 perfectly at the exact same time. And here's the crucial physical bottleneck. We have this massive, ever-growing flow of transaction execution just battling against a straining data infrastructure. And you can't just slap a Band-Aid on it by increasing block sizes to fit more transactions. Doing that means every individual node needs massive, incredibly expensive hardware just to store and process the data. And the moment you do that, you completely kill decentralization, which leads us to the ultimate hidden bottleneck of the whole system: data availability, or DA. This is the cryptographic guarantee that data is actually published and accessible. Think about it. Without accessible data, the entire concept of settlement loses its meaning. You can execute transactions lightning fast, but if nobody can actually get their hands on the data to independently verify it, the trust is completely gone.
Moving right along to Section 3, the modular reveal, fracturing the architecture. Now, watch what happens as that visual tension finally breaks. This right here is the exact aha moment for blockchain architects. On the left, you have your classic monolithic column, everything crammed into one single box. But on the right, that's the modular stack,
We are taking those 4 core functions we talked about and literally fracturing them into a composable stack of specialized networks. This horizontal expansion builds a totally flexible ecosystem. Execution gets moved off to independent chains called rollups. Settlement is safely anchored on highly secure layer 1s like Ethereum. Consensus gets decoupled for maximum flexibility. And we introduce dedicated data availability networks. The beauty of this? Each layer only has to be perfect at one specific job. It doesn't have to balance that trilemma all by itself anymore.
Section 4. Scaling with rollups. Taking computation off-chain. Zooming all the way into that top execution layer, we find the 2 dominant environments that are completely reshaping our scaling assumptions. Optimistic rollups and zero-knowledge or ZK rollups. These guys process thousands of transactions totally off the main base layer, bundle them all up, and then post just the proofs, the tiny summaries, back down to the settlement layer.
Let's compare them real quick. Optimistic rollups take a valid unless proven fraud approach. They just assume transactions are good, but they leave a dispute window, usually up to 7 days, for anyone to flag an error using a fraud proof. ZK rollups, on the flip side, demand mathematical certainty from the jump. They use some seriously complex cryptography to prove validity upfront. So finality is achieved instantly once that proof hits the blockchain. But the main takeaway? Both of them drastically reduce the heavy lifting on the main network.
Section 5. Solving data availability. The power of sampling.
Now, shifting our focus back down to the foundational layer, how do we handle all that data without crushing the participants? The secret weapon is data availability sampling, or DAS. It's an ingenious mathematical technique using erasure coding that lets lightweight nodes, literally just a regular laptop, verify huge data sets by downloading tiny random fractions of a block. If you sample just a tiny fraction of a percent of the data, the math actually guarantees with 99.99% certainty that the entire block is available. This is absolutely wild because it means the system gets more efficient as the blocks get bigger. And this exact breakthrough is what enables specialized DA networks like Celestia. Celestia takes consensus and data availability and completely isolates them from smart contract execution. It basically acts as a pluggable, modular data layer, so developers can launch their own rollups seamlessly without weighing down the settlement layer with massive storage requirements. It's a real game changer.
Finally, Section 6. A planetary scale future. Competing infrastructures.
If we pull the camera all the way back to a planetary scale view, we are basically witnessing a tale of 2 distinct infrastructures being built right now. On one side, we have monolithic refinement, networks pushing hardware limits to the absolute maximum to achieve incredible single-layer efficiency. On the other side, we have modular expansion, building a horizontal, interconnected ecosystem of specialized layers. Now, to be clear, we aren't taking sides here. Both are incredibly viable, highly competitive approaches, solving the exact same problem in beautifully different ways.
But the realization here is profound. There's a great quote that sums this up. The modularity theory proposes that the core functions of modern blockchains should themselves be disaggregated, allowing for tweaks and maximizations that increase the efficiency of each while sacrificing the fidelity of none. It means the future of scaling isn't just about writing faster code anymore. It's a fundamental structural redesign.
Which brings us to our final provocative thought. As we watch these countless modular networks expand endlessly into digital space, forming this massive interoperable ecosystem, we have to wonder, if the future of scalability requires fracturing the foundation to build something stronger, which architecture will ultimately become the definitive global trust machine, the all-in-one monolith, or the highly specialized modular stack? Thank you so much for exploring this with me in today's Explainer, and I'll see you next time.